This is the story of a point of light, a cosmic phantom that fooled some of the most powerful telescopes ever built, and in doing so rewrote our understanding of what it means to be a visitor from the stars. It begins, as all good cosmic mysteries do, with a flicker in the darkness. A single, unassuming white dot, racing through our solar system at a mind-bending 209,000 kilometers per hour. That's fast enough to travel from New York to Los Angeles in just over a minute. This wasn't just any space rock. Astronomers tracked its path, running the orbital calculations again and again, but the numbers refused to make sense. The trajectory didn't loop back around our sun. It was a hyperbola, an open-ended arc that screamed it was not from here. It was an outsider, a wanderer from the vast, dark expanse between the stars. On July 1, 2025, the Minor Planet Center made it official. This object, designated 3I Atlas, was only the third interstellar visitor ever confirmed. The excitement in the astronomical community was electric. We had another chance, another precious sample from a distant, unknown star system delivered right to our celestial doorstep. But the real story, the one that would unravel a mystery nobody even knew existed, had already begun 2 months earlier, buried in a mountain of data that no one was looking at. Enter the Transiting Exoplanet Survey Satellite, or TESS. TESS is NASA's planet hunter. Its job is to stare at vast patches of the sky for weeks at a time, looking for the faintest, most minuscule dips in starlight that might indicate a planet passing in front of its star. It wasn't designed to hunt for comets, but as fate would have it, from May 7th to June 1st, 2025, while 3I Atlas was still an anonymous dot on its way in, it drifted right through TESS's field of view. When scientists, spurred by the July discovery, realized this, they embarked on a kind of digital archaeology. They dug back into the TESS archives, a treasure trove of images taken every 2 minutes. What they found sent a shockwave through their understanding of comets. There it was, clear as day in the May data. The visitor was already glowing, already active. And it was doing so at an astonishing distance, 6.4 astronomical units from the Sun. To put that into perspective, 1 astronomical unit, or AU, is the distance from the Earth to the Sun. 6.4 AU is a place deep in the freezer of our solar system, far beyond the orbit of Mars, out where Jupiter reigns. At this distance, the Sun is a pale, weakened star. It's so cold that water, the very lifeblood of most comets we know, is frozen harder than granite. A comet out here should be a silent, sleeping snowball, a dark, inactive nucleus tumbling through space. But 3I Atlas was not asleep. It was wide awake and shining brightly. This was the first part of the puzzle. The second part was what made it a true enigma. Knowing it was active, the researchers' next logical step was to look for the evidence of that activity. The unmistakable signature of an active comet is its coma. Think of the coma as a comet's atmosphere, a vast, hazy cloud of gas and dust that erupts from the nucleus as it is heated by the sun. It's what gives comets their ghostly, ethereal appearance, what distinguishes them from a common asteroid. To find this coma, the science team stacked over 9,000 individual TESS images. This process is like taking thousands of short-exposure photographs of a faint object and layering them perfectly on top of one another. The result is one incredibly deep, sensitive image, capable of revealing the faintest, most delicate structures. They held their collective breath, expecting to see a fuzzy halo, a ghostly shroud of dust spreading out from the central point. They found nothing, absolutely nothing. There was no extended coma, no obvious cloud of gas and dust, just a sharp, brilliant point of light that looked, for all the world, exactly like a boring, inactive asteroid. This was the paradox that defined 3I Atlas. The object's brightness screamed, "I am an active comet," but its appearance whispered, "I am just a rock." The mystery wasn't whether it was awake. It was how, in the name of all cosmic laws, It was so perfectly hiding what it was doing. This is a profound question that extends far beyond the realm of astronomy, isn't it? It forces us to confront the limitations of our own perception. How many times in our own lives are we presented with a situation where the data just doesn't add up, where what we see with our own eyes is in direct contradiction with what other evidence is telling us? Maybe it's a friend whose words are cheerful, but whose eyes betray a deep sadness, or a project at work that looks perfect on the surface, but you have a nagging feeling that a fundamental flaw is being overlooked. We often dismiss these contradictions. We choose the simpler explanation, the one that fits our expectations. The story of Three-Eye Atlas is a powerful lesson in what can be discovered when we refuse to accept the simple explanation. It's a testament to the idea that sometimes the most profound truths are hidden not in the shadows, but in plain sight, camouflaged as something ordinary. What point of light in your life, something you've dismissed as simple and understood, might be hiding a universe of unseen activity? The initial discovery of this contradiction was just the beginning of the investigation. It was one thing to identify the paradox. It was another entirely to solve it. This is where the story shifts from one of cosmic mystery to one of human ingenuity and relentless scientific detective work. Imagine being on one of those research teams. You have two sets of irrefutable data on your screen. One says active, the other says inactive. They cannot both be right in the way you understand the universe. What do? You don't throw out the data. You throw out your assumptions. You dive deeper. Two teams working independently took on this challenge. One team, led by Adina Feinstein at Michigan State, knew TESS had been pointed at that region of space and immediately went hunting in the archives. Another, led by Martinez Palomera, would later publish their own analysis confirming the findings. Their primary tool was a technique called the shift-stack method. Let's break down what that means because it is a beautiful example of how scientists can pull a whisper of a signal out of a roar of noise. TESS takes an image every 2 minutes. In those 2 minutes, an object like Three-Eye Atlas, moving at 209,000 km/h, has traveled a significant distance across the camera's detector. If you just stacked the raw images, the comet would be a long, faint streak, its light smeared out and lost. The shift-stack method is a digital correction. The software identifies the object in every single frame, and then shifts each image so that the comet is perfectly aligned in the center. It's the digital equivalent of a sports photographer panning their camera to keep a racing car perfectly in focus. When you then stack these thousands of perfectly aligned images, the random noise of space, the faint background stars, the cosmic ray hits, averages out and fades away. But the light from the comet, now stationary in every frame, adds up. It grows stronger, more intense, more detailed with every layer. It's how you turn 9,000 fleeting glimpses into one long, deep stare. With their powerfully deep image constructed, the teams then performed what's called a radial profile analysis. This sounds complex, but the idea is simple. They drew a virtual line from the absolute center of the object outwards and measured how the brightness fell off with distance. For an object with a coma, you'd expect the brightness to be most intense at the center, and then fade away gradually, gently, as the dusty halo thins out. For a simple point source, like a star or an inactive asteroid, the brightness drops off incredibly sharply, almost immediately. The researchers performed this analysis on Three-Eye Atlas. Then, for comparison, they did the exact same thing for 4 known inactive asteroids that just happened to be in the same field of view. They laid the graphs on top of each other. The profiles were identical, perfect matches. No halo, no fuzz, no extended glow. Three-Eye Atlas matched the profile of a dead rock perfectly. This should have been the end of it. The visual evidence was overwhelming. But then there was the inconvenient truth of its brightness. The object was glowing with an absolute magnitude that was completely consistent with the Hubble Space Telescope's observations from July, when Hubble, a far more powerful and higher-resolution instrument, could clearly see a bright, dusty cocoon, a definite coma. The comet hadn't just suddenly roared to life between the TESS observations in May and the Hubble observations in July. The brightness numbers proved it was active the whole time. The conclusion was inescapable. The coma had to be there in May. TESS just couldn't see it. This is a critical lesson in problem solving and in life. It's the moment when you realize the problem isn't with the evidence, but with your tool or your perspective. It's like searching for a lost key in a dark room with a narrow beam flashlight. Just because you don't see it in the beam doesn't mean it's not in the room. You have to ask, is my tool right for this job? Is my perspective too narrow? The scientists looking at 3i Atlas realized their tool, TESS, with its large pixels designed for seeing broad changes in starlight, was the narrow beam flashlight. The coma wasn't absent. It was simply hiding in a way that TESS was blind to. This realization is a powerful metaphor for our own lives. How often do we declare something impossible or non-existent simply because our current methods or mindset can't perceive it? Think about a goal you've given up on, or a person you've written off. Is it possible that you were just using the wrong tool to see the potential that was there all along? The investigation into 3i Atlas teaches us that true breakthroughs often come not from finding new evidence, but from finding a new way to look at the evidence we already have. It's about having the courage to question our own perception and to believe in the data, even when it leads us into territory that seems completely paradoxical. So, how does a comet hide? How does it build a cloak of invisibility around its own activity? The answer, when it finally came, was both elegantly simple and profoundly revolutionary. It wasn't magic, it was physics. The solution to the paradox lay not in what the comet was made of, but in how it was throwing that material into space. The research teams, now armed with the certainty that a coma must have been present in May, worked backwards. They asked themselves, what physical conditions would have to be true for a coma to exist, but be undetectable to TESS? The conclusion they reached is what makes this story so compelling. The dust ejection velocity must have been extremely low. Let's visualize this. A typical comet, as it gets closer to the sun, is a violent, chaotic object. Water ice beneath its surface flash boils into gas, erupting into space like a geyser. This violent outgassing acts like a rocket engine, blasting dust and ice particles away from the nucleus at high speeds, anywhere from 20 to 100 meters per second. This is what creates the vast, spreading, easily visible coma that we associate with comets. Now, imagine a different scenario. Imagine instead of a violent geyser, the gas is seeping out gently, like air from a slow puncture. This gentle, low-pressure gas can't hurl dust particles into space. It can only gently lift them, giving them a slow, lazy push. The researchers calculated that if 3i Atlas was ejecting dust at a velocity of less than 10 meters per second, the material would not spread out. It would stay close, forming a tight, compact, dense cloud clinging to the nucleus like a shroud. A coma in miniature. This was the aha moment. This was the key that unlocked the entire mystery. The comet wasn't hiding its coma. Its coma was just incredibly small. The researchers did the math. A dust particle traveling at less than 10 nanometers for the 20 days TESS was watching would travel less than 17,000 kilometers from the nucleus. This sounds like a lot, but now consider the distance. 3i Atlas was 960 million kilometers away from TESS. From that immense distance, a 17,000-kilometer wide coma would subtend an angle of only about 2 arcseconds in the sky. And here, as the crucial detail, a single pixel on the TESS camera covers an area of 21 arcseconds. The entire active coma was more than 10 times smaller than one single pixel on the detector that was observing it. It was, in astronomical terms, unresolvable. The light from the nucleus and the light from the tiny coma all fell into the same single pixel. It couldn't be seen as a fuzzy, extended object because all its light was concentrated into a single point. It was hiding in plain sight. Its disguise was its own compactness. This discovery is a beautiful lesson in the importance of scale and perspective. What looks like one thing from a distance can be something entirely different when you zoom in. It reminds me of the pointillist paintings of Georges Seurat. If you stand far back from it a Sunday afternoon on the island of La Grande Jatte, you see people, trees, a cohesive scene. But if you step closer, right up to the canvas, you realize it's not a scene at all. It's just a collection of thousands of individual distinct dots of color. Your brain combines those dots into a single image. TESS was standing too far back. It saw the single point of light, but the researchers, through their analysis, were able to step closer and see that the point was actually a composite, a nucleus and its secret, compact coma. This has a powerful application in our daily lives. How often do we judge a situation or a person based on a single pixel view? We see one action, one comment, one event, and we draw a massive conclusion about the whole picture. We fail to resolve the complexity. We see the point of light, but miss the hidden coma of context, history, and subtle details that truly define what's going on. The story of 3I Atlas is a call to develop a higher resolution in our own empathy and understanding. It urges us to remember that beneath every simple surface, there is often a complex, dynamic system at play. It teaches us that some of the most powerful forces and the most important truths don't announce themselves with a shout. They operate quietly, compactly, with a low velocity that requires us to look with more than just our eyes. We have to look with our minds, with our curiosity, and with a willingness to believe that there is more to the story than what the first glance reveals. What are the compact comas in your life? The subtle, persistent patterns of behavior in yourself or others that might be revealing a much deeper truth, if only you could learn to resolve them. The discovery of the compact coma answered the how, but it left open an even more tantalizing question. Why? Why was this comet behaving so differently from nearly every other comet we've ever seen? Why the gentle lift instead of the violent blast? To answer that, we needed to know what it was made of. We needed to perform a cosmic chemical analysis. And for that, humanity had the perfect tool. The James Webb Space Telescope, JWST. On August 6, 2025, Webb turned its powerful infrared eye towards 3I Atlas, and what it saw provided the final, crucial piece of the puzzle. The results were stunning. The comet's coma was overwhelmingly dominated by a substance we all know, but don't typically associate with cometary fireworks: carbon dioxide. When Webb's instruments analyzed the infrared light from the coma, they found a staggering ratio of carbon dioxide, CO2, to water, H2O, of nearly 8:1. To be clear, this is utterly bizarre. Most comets from our own solar system are the other way around. They are giant, dirty snowballs dominated by water ice, with CO2 being a minor ingredient, often with ratios of 1:10 or even 1:20. 3I Atlas had flipped the recipe completely. It wasn't a dirty snowball, it was a dirty, dry ice ball. And this one chemical fact explained everything about its strange early behavior. Here's why. The behavior of any ice is determined by its sublimation point, the temperature at which it turns directly from a solid into a gas. For water ice, that process doesn't really get going until the temperature climbs to around 170 Kelvin, 103 odors, or 154 degrees. A comet needs to get relatively close to the Sun, typically inside the orbit of Mars, to get that warm. Carbon dioxide, however, is far more volatile. Its sublimation point is a frigid 60 Kelvin, 213 Celsius, or 352 degrees. Out at 6.4 AU, where TESS first saw 3I Atlas, The equilibrium temperature for a dark object is around 65 Kelvin. It was far, far too cold for water to do anything, but for carbon dioxide, it was perfect beach weather. The faint, distant sunlight was just enough to gently warm the surface to the exact temperature needed to make the CO2 ice begin to fizz, turning slowly and steadily from a solid into a gas. This explains the low velocity. The sublimation of CO2 at these low temperatures doesn't create a violent, high-pressure jet like flash-boiling water does. It creates a gentle, low-pressure, steady outgassing. This steady but weak gas flow was just strong enough to lift dust grains off the surface, but it didn't have the oomph to fling them far into space. And if those dust grains were particularly large and heavy, which later Hubble images suggested they were, the effect would be even more pronounced. A weak push against a heavy object results in a very slow acceleration. The physics was perfect. The CO2 dominance was the root cause of the gentle gas pressure, which was the root cause of the low dust velocity, which was the root cause of the compact coma, which was the root cause of the comet's brilliant disguise. The entire chain of logic snapped into place. This process of tracing an effect back to its root cause is one of the most powerful problem-solving tools we have, not just in science, but in our own lives. We so often get stuck treating symptoms without ever understanding the underlying disease. Imagine you're constantly tired. You might try drinking more coffee, treating the symptom, but you'll never feel truly rested until you diagnose the root cause. Maybe it's poor sleep, stress, or diet. 3I Atlas teaches us to be like the JWST. It encourages us to look deeper, beyond the surface behavior, to understand the fundamental chemical composition of the problems we face. When you're dealing with a recurring issue at work, a persistent conflict in a relationship, or a personal habit you can't seem to break, ask yourself, what is the CO2? What is the fundamental underlying driver that is causing all the surface-level effects? So often, we blame the low dust velocity, the immediate, visible problem, without realizing it's just a consequence of a much deeper, unseen chemical imbalance. If you can identify and address the root cause, the symptomatic problems often resolve themselves with surprising ease. It's a shift from being reactive to being diagnostic, and it is the key to solving our most stubborn and complex challenges. With the central mystery solved, the story of 3I Atlas expands, rocketing from a clever celestial puzzle into a profound, epic narrative about time, distance, and our place in the cosmos. This was no ordinary comet. Its extreme, hyperbolic trajectory wasn't just a sign that it came from another star. It was a clue to just how long it had been traveling. When astronomers traced its path backward, it didn't point to any single nearby star. Its journey had been too long, its path too altered by the subtle gravitational tugs of countless stars and nebulae over untold eons. The comet's high speed was the ultimate giveaway. Objects native to our solar system drift in from our own Oort cloud at relatively sedate speeds. 3I Atlas came screaming in at more than double that speed. This extra velocity is the hallmark of a truly ancient wanderer. Every close pass of a star, or a giant molecular cloud over millions of years, acts as a tiny gravitational slingshot, adding a little more speed. The faster the object, the longer its journey has likely been. Based on its trajectory, some astronomers have estimated that 3I Atlas may have originated in the galactic bulge, the dense, ancient core of the Milky Way. This suggests the comet could be up to 7 billion years old. 7 billion years. That means it likely formed around a star that ignited and died 2.5 billion years before our own sun even flickered into existence. It is, quite possibly, the oldest comet humanity has ever observed. It is a fossil, not of rock, but of ice and gas, a pristine, deep-frozen sample from a solar system that belonged to a younger, different Milky Way. It was then ejected, cast out from its home system by the gravitational chaos of forming planets, and sent on an unimaginable journey through the dark. For billions of years, it drifted through the void, enduring the silent bombardment of cosmic rays, a silent witness to the birth and death of stars around it. Then, by pure, beautiful chance, its multi-billion-year path intersected with a tiny, one-in-a-trillion speck of space containing our solar system. And the secrets it carried were not just in its CO2. The James Webb telescope also detected other strange chemicals, including a molecule called nickel carbonyl. This rare, complex molecule, if confirmed, would be a first in any comet and hints at an incredibly cold, carbon-rich formation environment, or perhaps chemical reactions that occurred on its surface during its long, cold journey through interstellar clouds. Furthermore, other telescopes detected the clear signature of large, 10-micrometer water ice grains floating in its coma. This is also unusual. It suggests the nucleus isn't just releasing gas, it's shedding chunks of ice, which then sublimate in the space around it, creating a secondary, extended source of water vapor. Every new observation added another layer of beautiful weirdness, painting a picture of an object fundamentally different from the ones we call our own. This is the ultimate lesson of 3i Atlas. It is a lesson in perspective and empathy. It's so easy to get consumed by the urgency and scale of our own lives, our deadlines, our worries, our conflicts. We see the world through the pinhole of our own experience. The story of this comet is a powerful antidote to that. It is a physical manifestation of deep time and vast space. It reminds us that our world, our history, our entire species, is just a brief flicker in the life of one ancient piece of ice. But instead of making us feel insignificant, this perspective can be profoundly liberating and connecting. It gives us a sense of being part of a much grander, much older story. More than that, it can change how we see each other. Every person you meet has, in a sense, been on their own interstellar journey. They carry an unseen history, a unique path through time and experience that has shaped them in ways you can't possibly see on the surface. We see their point of light in the present, but we are blind to the billions of moments, the gravitational tugs of past joys and sorrows that brought them to where they are. When you face a person you don't understand, or whose behavior seems alien, try to remember 3i Atlas. Consider the vast unseen history they carry. Approach them not with judgment based on their morphology, but with the curiosity of a scientist encountering a visitor from another world. Ask questions. Seek to understand their chemical composition. This is the foundation of empathy. It is the recognition that every point of light contains a universe of hidden complexity. The story of 3i Atlas began as a mystery about a single point of light, but it ends as a lesson for all of us. It teaches us to challenge our assumptions and to look for the evidence that contradicts our beliefs. It teaches us to dig deeper, to revisit old data with new eyes, and to appreciate the power of scientific detective work. It teaches us to look for the subtle, compact, low-velocity signals in our lives that may reveal a far greater truth than the loud, obvious events. It teaches us to diagnose root causes instead of just treating symptoms. And most of all, it teaches us to look at the world and at each other with a sense of wonder, recognizing the vast, unseen history that makes everything and everyone so much more than what they appear to be on the surface. Thank you for joining me on this incredible journey to the outer edges of our solar system and back. I hope this story has left you with a renewed sense of wonder about the universe and our connection to it. Take care of yourselves and be well. And if you value deep, evidence-based stories about science and the human experience, please consider subscribing. It is the best way to support our work and ensure we can continue to explore these cosmic mysteries together.